Our next speaker and last speaker for this technical session is Dr. Elina Nayebi. Dr. Elina Nayebi received her BS in Electrical Engineering from the University of Tehran in Iran in 2012 and MS and PhD degrees in Electrical and Computer Engineering at UCSD in 2015 and 2018 respectively. She has over half a decade of industry experience, including multiple internships at Nokia Bell Labs and Qualcomm Technologies, and full-time positions at Samsung Semiconductor and Apple, where she is the systems engineer. So I invite Dr. Elina. Thank you.
It's an honor to be here and speaking in this event. I had the honor of being Professor Rao's PhD student since from 2012 to 2017. I have a lot of fond memories from my PhD when I was in Professor Rao's lab, but I was asked to deliver a technical presentation, so I'm gonna focus on two of the topics that I worked with Professor Rao while I was doing my PhD. So the first topic is pre-coding and power optimization in self-free massive MIMO systems. So I'd like to mention that this was a joint work with Tom Marzetta, Alexei Eshekmin, and Hong Yang from Bell Labs, and Professor Rao and me. So when we started working on this problem, the massive MIMO systems with co-located antennas, they were well studied and understood, but there was not much work done for the distributed systems. So we wanted to know what happens if we have a large number of antennas that are distributed in a designated area. So compared with the co-located antennas, there are some advantages and disadvantages for the distributed systems. For the co-located antennas, most users are far away from access points, whereas in the distributed system, there is a high probability that you are close to an access point. And in the co-located systems, we cannot increase the antenna array size infinitely large. As we keep adding more number of antennas, there's going to be some point that the antennas are getting closer to each other. So this creates rank deficiency in the channel matrix. So there's no point in adding more antennas anymore. However, we don't have that problem in the distributed systems. And in co-located systems, there might be cases that a user has some unfavorable shadowing. For example, there's a building between you and the base station. So you're just going to have to wait so the channel changes, user moves, so that the channel gets better. But that's not the case in the distributed systems. However, in this case, when antennas are distributed, you need a reliable backhaul network, and you also need good synchronization between the antennas because everybody needs to know what they are going to transmit to a user. So we called these distributed systems with a large number of antennas cell-free systems because there is no notion of cell here. Here we assume that large number of antennas are serving a much smaller number of users simultaneously. So the main difference between cell-free systems and a regular co-located MIMO system is basically in the channel definition. In the co-located system channel, let me say that we here assume that we have OFDM systems so that the channel is flat fading. So the channel between antennas and user K can be written as like large scale fading, beta times a small scale fading coefficients. This H here is a vector. It is the channel for all of the antennas, but all of the antennas with user K only have one large scale fading because they are co-located. However, in the distributed system, each pair of user antenna has its own large scale fading coefficient. So basically, that's the main difference between two systems. So in this work, in order to compare with other systems, we considered like two extreme scenarios. The cell-free case, when all of the antennas are serving all of the users. So all the antennas are connected to each other or to a network controller that tells them what to transmit, etc. And the other end of the spectrum, which is a small cell, where each user is only served by one access point. So we wanted to compare the performance between these two and see how much we gain from collaboration in massive MIMO type of scenario. When we have infinitely large number of antennas, M single antenna access point or antennas that are much larger than number of the K single antenna users. In this work, the goal is to obtain achievable rate. So we wanted to see what type of rates we can get. And we also wanted to use power control to optimize and maximize the data rates that the users can experience. We already went over the channel model. G between antenna M and user K is beta times H. Beta is large scale fading and accounts for path loss and shadowing effects. And we assume it's already known because these coefficients are typically change slowly, so we can learn them pretty good. So at the first step, what happens is that users send orthogonal pilot sequences to the access points, and each access point learns the channel between itself and all users using MMSE estimates, like given here. So in order to get the achievable rate, we looked at two precoders. One was conjugate beamforming, where each antenna transmits to all users by just simply using the conjugate of the channel between itself and the user and transmitting data to the user, and the summation over all Ks because we are serving all users. Here rho is the total power that each antenna is allowed to transmit. And eta mi is the fraction of the power that access point M can allocate to user I. And the goal of our optimization in the power control is to find these etas, how to allocate these powers between different users so that we can maximize the rate. So here we have this theorem that this is a lower bound on capacity or achievable rate. That is log of 1 plus SINR, and SINR is given here. The interesting thing about this SINR is that it doesn't contain any small scale fading coefficients. They all average out, and we are left with only the large scale fading coefficients. This is the beauty of massive MIMO, that as you increase the number of antennas, you don't have to deal with the small scale fading. Only working with the large scale fading is enough. And so our power control needs to be only updated when these betas change, which is not that often. We had similar notion for zero forcing, but I think we are short on time, so I'm gonna skip these. But basically, the idea was the same. So now for the power control, we are interested to serve all users with similar performance. So in order to achieve that, we used max min power optimization or allocation by simply trying to find the optimal etas, power coefficients, that maximize the minimum rate among all users with per antenna power constraints. This is for conjugate beamforming, this is for zero forcing. So we showed that these problems are actually quasi-concave, and we can solve them by using bisection method, but bisection method is very not efficient. It's iterative method. You need to solve a convex feasibility problem at each iteration. So we had several ideas to simplify these problems, and I think, we have multiple options to simplify these problems and even get closed form solutions. And we had a couple of lemmas showing that how tight these approximations are to the actual answer. So I'm skipping these slides because, I don't have time to go through the details. Okay, so now let's look at the cell-free system. We wanted to compare the small cell system. So we wanted to compare the cell-free with the small cell. So here the idea is that we are only served by one access point. A simple choice of access point could be the one that has the largest scale fading among the all access points. So similarly, we derived the achievable rate for this system. Here the SINR is given here, and you can see that here actually the rate depends on both small and large scale fading. This is because we don't have infinite number of antennas, so we cannot rely on channel hardening effect. So the power optimization needs to be done when this G changes, which is pretty often. Some simulation results here. So here we have a CDF of the achievable rates. We assume that we have like randomly located users and antennas, and we do thousands of iterations and then collect all the achievable rates of the all users and plot the CDF. This red line here is cell-free zero forcing. The blue here is cell-free conjugate beamforming, and the green here is the small cell data rate. So we are in particular interested in the 5% outage rate, which is shown here by this vertical line. 5% outage rate is basically tells us what are the poor guys do. So the smallest rate among 95% of the best users. If we look at this rate by going from small cell to cell-free conjugate beamforming and to zero forcing, we see 5 to 10-fold improvement, which is huge. So small cell-free systems can help a lot. They can help they can help give users uniformly good service. Whereas in the small cell, you can see that it contains a lot of rates. The range of the rates that the users can get is quite large. Sometimes they get pretty good rates, but a lot of times they get a lot of bad rates. So the beauty of massive MIMO and cell-free massive MIMO is that we are getting consistently good rates for all users. Okay, so before I move to the next topic, just wanted to mention that since we worked on this problem, there has been lots of traction to cell-free massive MIMO systems, and they're considered as one of the candidates for 6G. The next topic is semi-blind channel estimation for massive MIMO systems. Okay, so in order to achieve all these data rates that are promised by massive MIMO, we need to have a good channel state information. One way to get it is to transmit pilot sequences that are known at the receiver, and then the receiver uses that to estimate the channel and then uses that channel to decode this data. Other option is to actually use this data portion as well, because once we get these pilots, we know on some level what this data is. So we can use this data to improve our channel estimates, to get even better channel estimates. Or some could say, let's keep the accuracy the same as before, but use smaller number of pilots so that we can allocate more time to the data and increase the throughput. Massive MIMO systems can benefit from this semi-blind channel estimation in both uplink and downlink, because most emphasis for massive MIMO is in TDD systems, where uplink and downlink channels are the same. So that's why we wanted to look at semi-blind channel estimation, in particular for massive MIMO systems. Here, the system model, we have a single cell and antennas are actually co-located here. The channel model is similar to the previous case, smaller scale fading and larger scale fading. So we assume that users are transmitting orthogonal pilots, and this is uplink transmission. And the base station receives signal Y, which is G channel times the transmitted signal plus noise. For the first L symbols, we are transmitting pilots. And the next n minus L symbols are the data symbols. And similarly, for the received signal, we call this portion Y pilot and Y data. So we compared the performance of this semi-blind channel estimators with two maximum likelihood estimators. One of them is just using the pilots and do maximum likelihood estimation. This has a nice closed form solution. And then the other one is gene-aided channel estimation, where we assume that we also know the data. It's perfectly known. So this is going to serve us as an upper bound for what we can achieve. So the semi-blind estimation is going to be something in between these two. And we wanted to see, like, for massive MIMO, as we increase number of antennas, how are we? Are we close to this point, or can we get closer to the gene-aided case? These two have closed form solutions, but the semi-blind problem turns out that it's not very easy to solve. The log likelihood of the received signal, Y pilot and Y data, given that we only know the pilots, is an incomplete data. So there are suboptimal ways to solve it. We actually looked at solving this with expectation maximization algorithm, which is to basically augment the hidden data, S data, to the received signal, and then later taking the expected value with respect to the posterior of the hidden variable given previous estimates of the channel. So this will be an iterative solution, and this is going to be the maximization step. The result is given here. If you look at this equation, you will see that the first two portions in these two parentheses are for pilot portions, and the second two are for the data portion. And we will need to take the expected value of data and like the first and second norm of the data given the previous estimate of the channel. This is the M step. For E step, usually these data symbols come from a discrete constellation. But if we use the actual discrete constellation, this E step is going to be very complex. So in order to solve this problem, we looked at different actually distributions or priors on data. So one was Gaussian prior, and the other one was Gaussian mixture prior, and another heuristic model. I want to skip this part, but just want to mention that with all of these options, with three options, we arrived at nice closed form solutions for E and M steps that after iterating through them, we are going to get pretty good channel estimates. Okay, so that was how to get the channel estimates, but how about the performance? Where are we? Like, in order to answer that, we looked at Kramer-Rao lower bounds for this estimator, semi-blind estimator. And in particular, we were interested to see how these Kramer-Rao lower bounds will behave as we increase the number of antennas. So I'm not going to bore you with the details. It's just that I want to show you that as we increase the number of antennas, we can show these CRB converges to CRB of a gene-aided system, meaning that as we increase the number of antennas, it is as if we know the data symbols as well perfectly. This was a deterministic CRB. We also looked at a stochastic CRB, where we assume that data symbols are from Gaussian distribution, and we observed the same result, that CRB, as we increase the number of antennas, converges to an I matrix, which is equivalent to CRB of a system with orthogonal pilots of length n, which is the length of both pilots and data. This is very interesting for massive MIMO systems, because in massive MIMO, there is this notion of pilot contamination, which limits the overall performance and the achievable rate. But with this result, we can show that if we use the semi-blind channel estimation, it's as if we are increasing the length of the pilot sequences. And the pilot contamination problem comes because the length of the pilots are not orthogonal, because we don't have enough orthogonal pilots. But if the length, equivalent length is increasing, it means that the number of orthogonal pilots are increasing, so we are alleviating the pilot contamination problem in the massive MIMO systems. We have several simulation results. I'm just gonna probably show one. Here we have mean squared error of channel versus M, number of antennas at the base station. The magenta curve here is when we only use the training sequence. The black one here is the gene-aided, which assumes that the receiver knows both pilots and data perfectly. And these three are our proposed algorithms, the EM algorithms with different priors. And the interesting result is that we are converging to the gene-aided case as we increase the number of antennas, and which coincides with our CRB results. We also had work on to show how much benefit we can get if we use these channel estimates in the downlink beamforming, but I'm gonna skip these. And yeah, with that, I conclude my presentation.